fans.
My name is Amiza Sajliana binti Mazini. My metric number is CF250105 from Group 2. I'm going to present about our project is fluid analysis of pipe network using Hadley cross method. Now, I will start our introduction for our project. A reliable water distribution system is inserted to ensure that sufficient water supply is delivered to use with adequate pressure and discharge. In complex pipes network containing multiple loops, analytical solution become difficult due to the interdependency between flow rate and head loss in each pipe. Therefore, an iterate technique known as the Hadley cross method is commonly used in fluid engineering to analyze the system. The Hadley cross method is based on the pipe principle of continuity at nodes and energy conservation around closed loop. By assuming integral flow rate at that signifies continuity, head loss, and calculate using empirical equation such as the Hazel-Williams formula. Correction and apply interacting until the algebra sum of head loss is H loop approaches 0. This project applied the Hadley cross method at the multi-loop pipe network using the Hazel-Williams equation to determine the final discharge in each pipe. Problem statement. The pipe network in this project consists of several interconnected loops with different pipe length and diameter, making the determination of flow distribution difficult using simple method. The inlet flow at node E must be correctly distributed at all outlet nodes while certifying continuity and energy conservation. Therefore, the Hadley cross method is used to analyze the pipe network and determine the flow rate in each pipe by applying interactive calculation with the Hazel-Williams head loss equation.
Assalamualaikum and hi. My name is Nufa Talib. My matrix number is CF250020. Today I will present about the objective of our project. The main objective of this project is to perform a complete hydraulic analysis of a multi-loop pipe network using the Hadley cross method. These pipe networks, which are common in local water distributions and industrial systems, will pose a significant issue because the flow in every single pipe is determined by the overall system structure and functioning. The objective is to systematically determine the unknown discharge in each pipe segment. This is not a simple calculation since the final solution must comply to two fundamental physical rules at the same time, which are mass conservation at every junction, which is not continuity, and energy conservation around each independent closed circuit. To achieve the goal, this project will use the Hadley cross method, which are a traditional technique that offers an organized step-by-step analytical approach. The approach determines modified flow rates for each loop based on an initial assumed flow distribution that ensure node continuity. These corrections are conducted continuously, slowly decreasing the net head loss around each loop to zero and thus ensuring energy conservation. This repeated procedure gives students hands-on experiences resolving interconnected hydraulic equations, which resembles the problem-solving workflows utilized in professional civil engineering practice for building and analyzing pipeline systems. The estimation of the fractional head losses within the pipes is an important part of the analysis. The project applies the Hazel-Williams equations and empirical calculations commonly utilized in water supply engineering. This equation connects head loss to pipe discharge, length and diameter with a coefficient to account for pipe materialness. By applying this equation to pipes of different sizes and conditions throughout the network, the project demonstrates how physical infrastructure characteristics such as all pipes with reduced roughness coefficient for other organic strategic use of larger diameters directly influence system pressures and flow distribution. So to conclude my objective, by manually repeating through the Hardy-Cross technique and applying the Hazen-Williams equations, we can gain more basic knowledge of hydraulic network behavior under various restrictions. This project not only reinforces fundamental principles of energy and mass conservation, but it also develops necessary abilities in analytical computing and analysis. This hands-on training is crucial in educating students to face real-world difficulties in water resource management and infrastructure design, where optimal flow distribution is critical to system efficiency and reliability. Thank you.
Assalamualaikum and hi everyone. My name is Noamira Shakira binti Azmi. My metric numbers is CF250097. So today I would like to present a project. It is about fluid analysis of pipe networks using Hardy-Cross method. So I'm continue of methodology. So for this project, we analyze a multi-log pipe network using the Hardy-Cross method. So first, we identify the pipe network layout, the intake flow, the outlet demands, and the pipe characteristic, such as length and diameter from the given data. So all value were converted into SI units to ensure consistency in the calculations. So next, we assume initial flow rates for each pipe while making sure that continuity was satisfied at every node, meaning the total inflow was equal to the total outflow. So after that, the Hazen-Williams equations was used to calculate the head loss in each pipe based on the assumed flow rates. So for each load, the algebra sum of head losses was determined. The flow correction value were calculated using the Hardy-Cross formula. So that corrections were applied interactively according to the flow directions until the correction values become very small. So at this point, the solution was considered coverage, and the final flow rates represent the actual flow distribution in the pipe network. So that's all for me. Thank you.
Next is pipe network analysis. The network originates at pipe E with an inflow of 100 liters per second. From here, water splits into ED, which is 80 liters per second, and EF, 20 liters per second. In the upper tier, DA carries 60 liters per second, while DC rolls 20 liters per second downwards. Pipe A discharges 30 liters per second externally, leaving 30 liters per second for AB. In the mix section, CB carries 15 liters per second, and FC moves 5 liters per second. For pipe F, exhausts 30 liters per second externally, and the lower segment include HF, 5 liters per second, and HL, 15 liters per second. Finally, the base shows LK with 5 liters per second, and pipe L discharging 20 liters per second, completing the distribution. Next is our calculation that we have done in Excel. First is to find the resistance coefficient K. F is referred to friction factor, L is referred to length of pipe in meter, D is diameter of pipe in meter, and for the 96.8208 is a constant likely derived from gravity and unit conversion. For KQ, represent the energy head loss due to friction as water moves through the pipe. In the Hardy-Cross method, N is typically 2 for Darcy-Weisberg. Lastly is for NKQ. The 2 indicates that the Darcy-Weisberg equation is being used. The absolute value is used because the term must be positive to ensure the iterative correction move toward the correct equilibrium. From trial 1 until trial 5, this iteration over and over until the correction factor dq becomes nearly zero, meaning the pipe network analysis is in balance. As a conclusion, hydraulic analysis of Town A's water distribution network was successfully completed. The Hardy-Gross method effectively balanced flow in an 18-pipe multi-loop duct system. Darcy-Weisbach equation was used to accurately calculate head losses. Iterative corrections ensured flow quantity and zero net head loss in closed loops. Proper pipe sizing for until 8 inches and reservoir placement improved system performance. Computational tools such as Microsoft Excel increase efficiency and reduce calculations error. The study provides a reliable foundation for a sustainable municipal water supply system.